Students, this is Unit 7 Circles, Lesson 7.5, Undercover Right Angles, Part 2. Take a look here. Make sure you are getting both the location, date, and time that you're watching this video. Make sure you get a parent or guardian sign off. It says in the diagram below, find all possible angle measures and arc measures. Make sure there's an and there. You have 2 minutes. Go. Your goal is to find all the angle and arc measures there. Okay, so we have here, let's take a look. This is the center of the circle. And we know, let's start with the basics. Measure of a central angle to its arc the same. So right there, if that's 165, this is 165. Then you should have noticed from here to here, that's a tan. That's going to be 360 minus 165. And that's 195 going this way. And then we have here, if tangent to a radius, if tangent to a radius, right angle at the edge. So you had right angles both here and here. And then this angle is a tan angle. And that angle equals big arc minus little arc over 2. And so our big arc, so our angle is going to equal our big arc 195 minus our little arc 165 over 2. And that's going to be 30 over 2. Therefore, our angle out here is 15 degrees. Okay, today, this is Undercover Right Angles Part 2. Before we leave today, you're going to be talking about circles, chords, arc, the word distance, congruent, and right triangle. Now, you think you know what that word means, but in a circle, it has a very specific meaning. So watch out for that word distance. It's not what you think it means. First, we're going to start with something simple. It says, draw two congruent chords, sweep the corresponding minor arcs. So we're going to draw two congruent chords, and we're going to sweep the corresponding minor arcs. So let's draw two chords. And they're congruent, so mark them congruent. Now sweep the corresponding arcs. Now you should see that if the chords are congruent, the arcs are also congruent to each other. If the chords are congruent, the arcs are congruent. The converse is also true. If the arcs are congruent, the chords are congruent. Since it's true going both directions, we call this a biconditional statement. Means whatever the statement is, it's true reading both one way and the converse is also true. That's called biconditional. You're going to need a straight edge here. First bullet says trace and sweep, EHF. Second bullet says draw in a radius HI so that it is a bisector of the angle EHF. We're supposed to trace and sweep EHF. Now we're going to draw a radius HI so that it cuts EHF in half. So that's being cut in half. There's a bisector. And this is HI. Next it says draw chord E to F. E to F. Mark the intersection of HI and EF as point W. Okay, this one you're going to have to do on your own. I'd like you to trace the chord EF and the radius HI and ask yourself, what do you notice? What do you notice? Trace the chord EF and HI. I'd like you to write, what do you notice? I'm not going to fill this in for you. There's a couple things you could notice there. Write down, what do you notice? I'm going to be quiet for about 20 seconds. The next one says, I'd like you to trace the segment EW and WF. Excuse me, EW, trace it, and WF. trace those segments. Put your pencil on your paper, actually trace those. Again, I'd like you to write, what do you personally notice? Okay, let's take a look here. I'd like you to draw in this diagram. Actually, in both diagrams, I'd like you to mark the center. And I'd like you to draw a radius. Now I'd like you to draw a chord which is perpendicular to that radius. Draw a chord which is perpendicular to the radius. And here I'd like you to draw a chord so that the radius cuts it in the middle. Okay, let's take a look at both of these really carefully here. Taking a look here, if we have a right angle there, I'd like you to trace these two segments and ask yourself, what do you notice? It's perpendicular, but what's going on with that? You should have noticed, wow, that's being bisected. And that is the main event where we get another undercover right angle. If a radius is perpendicular to a chord, then it bisects the chord. It cuts the chord in half. If perpendicular, then bisects. So if perpendicular, then bisect. And if you take a close look here, that is perpendicular. I'd like you to trace this angle. Can you feel that? You should be feeling that, wow, it bisected, then it's also perpendicular. So if a radius bisects a chord, then it's also perpendicular to the chord. So there is your third undercover right angle. So if perpendicular, then bisects. If bisects, then perpendicular. Now remember, whenever you have right angles, anything from your right triangle toolbox is fair game, which includes Pythagorean theorem, 45, 45, 90, 30, 60, 90, SOHCAHTOA, inverse SOHCAHTOA. We're going to do an example together. It says in circle A below, the radius length is 13 centimeters. Radius length A to E. So trace A to E. That's going to be 13 centimeters. And the length of B to D, the chord, is 10 centimeters. So ready, 10 centimeters. That whole thing is 10 centimeters. It says find all possible segment lengths and angle measures. Now you're like, wait a minute. There is no right triangles here. How can I solve? I do see a right angle, but I don't have any right triangles. And if I don't have a right triangle, I can't really solve for anything because right triangles are absolutely everything. So if you don't see a right triangle, you should always ask yourself, can you make one? Remember, you can always move, draw in, or add extra radii because all radii are congruent. Which means, can I add a radius so that I end up with a right triangle? I'm going to wait for you just about 20 seconds. The question is this: can you add a radius so that you end up creating a right triangle? Add a radius so that you end up creating a right triangle. I'm going to be quiet for 20 seconds and see if you can't get that yourself. Okay, again, your goal was to move a radius so that you could get a right triangle. And if you take that radius right there, you can move it. We're going to move that radius and draw it in from there to there. And behold, you have a right triangle. Remember, all radii are equal, so that is 13. And since it's perpendicular, it also bisects, so that means this is 5 centimeters and this is 5 centimeters. So from here, our goal is to find all possible segment lengths and angle measures. So now that we have a right triangle, we just start squeezing the sponge here. So let's deal with something that's easy to find, really easy to find. If I have a right triangle, I see here that's 13. And I have here that's 5. First thing I'm going to go for is that piece right there. And I don't know that. So that's 5 centimeters. That's a right angle. This is 13 centimeters. And this is going to be our x. Pythagorean theorem. I'm going to go 5 squared plus x squared equals 13 squared. Whoops, let me keep my color straight. That should be red. Yes, you may use a calculator just for speed's sake, but I'm going to probably beat you by the time you finish with your calculator, because I know my perfect squares. So we just found that x is 12. Now our goal is to find all possible segments. So let's pick off the easy one. That is a radius 2, so of course that's 13. Now to understand this, you need to trace with me. So put your pencil on A, trace A to E. Now trace that 12, trace A to E again, trace that 12. You should have remembered if from here to here is 13, that means from here to here is 1, because it's 13 minus 12. All right, you feel good about it. You found all segments. Woohoo! You found all segments, but you're not done. Because look what I asked you to also find. Angle measures. But Miss Way, there's no angles. How can I find angle measures? Remember, you have a right triangle. If you have a right triangle, there are 5 different tools you can use. Looky here. So you ask yourself, which one of these 5 tools are going to help you find angles? That's going to be inverse SOHCAHTOA. So I'm going to pull this triangle. Since I already have this triangle out, I'm going to find this green angle right here. And since I have all 3 sides, I could use sine, cosine, or tangent. I tend to default to sine. So it's inverse sine, opposite over hypo is going to give us our angle theta. Inverse sine, our opposite is 12. Our hypo is 13. It's going to give us that angle theta. Get out your calculators. You're going to do this with me. We do second function sine, 12 divided by 13. Hit the enter. My calculator goes backwards, so I'm going to go 12 divided by 13 equals inverse sine. I'm going to round to the nearest whole degree. That's 67. So this angle right here is 67 degrees. I got 90 there. I'm going to go 90 minus 67. It's 23. 23. You're like, yay, I'm done. I found all the angles. No, you didn't. Because now we have a central angle. And if that's 23, and that's a central angle, that means this arc out here is 23 degrees. And since this bisected, this arc over here has to be 23 degrees. Which makes it together 46. This is 180. That means this is 134. 134. Which means this angle right here is 134 degrees as well. Now you have found everything. I'm going to read this and I want you to try to draw it. That's all I want you to do. Read it and attempt to draw it. Just draw it. The chord AB is 5 centimeters from the center. The chord CD is also 5 centimeters in distance from the center. Attempt to draw that. If we have chord AB 5 centimeters from the center, that's code word for distance. And we always measure distance in a circle from the center. So if it's 5 centimeters, we would actually draw that segment right there, 5 centimeters. And if CD is 5 centimeters, we would draw it right like so. Curious if you drew it similar. It's really important you understand this. When we talk about a chord being a certain distance from the center, that distance is an actual segment. It's an actual segment. It's not just some ethereal measurement. It's a physical segment. Believe it or not, that segment has 2 qualities. 1. That distance segment always bisects the chord and creates a right angle. So in your diagram here, your distance from the center, it always bisects the chord, and it also creates a right angle. So there is another right angle you should watch out for. And the key word to find that right angle is the word distance, or from the center. We are told that chords B, E, and C, D are equal measure. Drawing the distance, remember the distance, that's going to hit a midpoint. So hatch marks, and it creates a right angle. If the chords are congruent, so notice the red segments, if the chords are congruent, then the distances is also congruent. Or equal, excuse me, we're dealing with measures here. If the chords are congruent, the distances are equal. So that means those are equal too. So your fourth undercover right angle is the word distance from the center. That's a segment. It's from the center. It hits a chord's midpoint, creates a right angle, and splits that chord in half. Okay, I'm going to read these bullets. I want you to try to draw them. Do this in pencil, so that I'm going to do this with you after the fact. It says we're going to, in the circle below, label the center P. So let's start with P. Draw in a radius P to Q, which is 5 centimeters in length. Excuse me, 15 centimeters in length. On the other side of the circle, draw in a chord AB, which is 9 centimeters from the center of the circle. Now that's the tricky one. We have AB here. And it is 9 centimeters from the center. Remember, that's a segment length that hits the midpoint and creates a right angle. That is 9 centimeters from the center. Notice it doesn't go all the way through. It's not a radius. Our goal is to find all possible segment lengths and angle and arc measures. Remember, you can always draw in extra radii. We're going to do this one together. Okay, once again, there's no right triangle there. You can't do anything without a right triangle. Right triangles are the key to the geometry universe. Right triangles. So if you don't see a right triangle, ask yourself, can you make one? And remember, we can always draw or move in radii. So if that's a radius here is 15, ask yourself, is there somewhere else you can draw that radius? Exact same radius, behold. Oh my goodness, looky there. It's a right triangle. Bring that 15 over. Now this is a squeeze a sponge problem, so your goal is to find everything that you can possibly find. So let's start by finding the squiggle. And we're going to use Pythagorean theorem, leg squared plus our unknown squiggle, I'll just use x squared equals 15 squared. Again, where did I get the 15? Because all radii are equal. Let's solve. Try to do your own math, see if you can't beat me. All right, let's see. That's 12. So that means that's 12. Okay, we have all current segment measures, but remember, we also want, we're done with segments, we also want angles and arcs. So let's see what we can find here. Let me pull this triangle out. Right there, you see that? Pull that out. That's 12, right angle, 9, 15. Let's start by finding that green angle. That's opposite, adjacent, hypo. I'm going to pause and let you catch up. Just for kicks, I'm going to switch it up and I'm going to use OA. I'm going to use opposite over adjacent. So inverse tan, opposite over adjacent is going to give us that angle theta. So use your own calculator so you know how to do this on your calculator. I'm going to do inverse tan, so I'm going to do 12 divided by 9, inverse tangent, and I get approximately 53 degrees. So we just found this angle, 53 degrees, which means we can do 90 minus 53. And we can find this angle up here, it's 37. And you think you're done. You're like, wow, I found everything. No, you did not. Because that 53 is connected to the center. So you can create a central angle. And that's 53 degrees. And that means the arc from here to here has to be 53 degrees. So you can sweep around and find that big arc by doing 360 minus 106. That's 2 times 53. Actually, don't have to borrow from that 3 there. So we get 254. Getting the hang of this? All right, you're going to do one on your own. That was the page. So this page right here, I'm going to set the timer for 2 minutes. And you're going to find everything that you possibly can find, both in segment lengths and angle measures. In fact, I'll give you 3 minutes because you might need that long. Ready? 3 minutes. Find everything that you can find. Go. Okay, let's see how you did here. Your goal was to find everything possible. So the first thing you should have noticed, if perpendicular then bisect, you should have had a 10 and a 10 here. So this is 10, that's 10. You're going to bring this 12 around. If 12 is here, it's also here. So I'm going to find x. So it's x squared, leg squared, plus the other leg squared equals the hypo squared, which is 12 squared. So we have x squared plus 100 equals 144. X squared equals 44. We square root. And we can have 2 and 22, 2 and 11. So that's 2 root 11. Or we're going to do 44 square root. And it's 6.6. You need to be familiar with both. I might ask you for both. 6.6. Now, we're going to find this angle right here. I'm going to use inverse sign. So, inverse sign. Actually, I'm going to use inverse cosine this time. You end up with the same thing. So, I'm going to use inverse cosine, my adjacent, which is 10, my hypo, which is 12. So 10 divided by 12, and inverse cosine. Get 33.5, so I'm going to round that up to 34. This is 34 degrees. You're like, wait a minute, that's not a central angle. It's not, but it is inscribed. So that means this out here is going to be 68 degrees. And I can also take 34 away from 90. And I'm going to get 56 here. And you should have noticed this is a diameter. So to get this arc, we simply do 180 minus 68. And that gets me 112. And then this way is really easy. It's just straight up 180. And now you have found all arcs and angles. Let's get out your reference booklet and fill a couple things in. Go back to the page you left off on, which would be right there. There was a space here on the right. Undercover right angles. It goes like this. If perpendicular, then bisect. And this is what's true, is if a chord is perpendicular to a radius, the radius bisects the chord. The converse is also true. If you have a distance that bisects a chord, then it's also going to be perpendicular. Then right here, underneath the tan angle, distance, remember distance is from center to that. Distance always bisects the chord, and it is also perpendicular to the chord. You can use the symbol there. The word distance is just the red there. That's coming up in the next video. All right, do a 2-minute verbal recap to yourself and you're done.